Hello everyone, this is the class notes on 16.3 half-life, and the relevant formula here is n is equal to n naught 1/2 to the power of n. Now in this case, n naught or NO stands for the original number. Now, or we'll say amount, like the original amount or the original number. N stands for the present number or amount. And this little n is the number of half-lives. Now again, the idea of a half-life is if I have 100% of something, after a certain amount of time, it's going to decay to 50%. Now, this is more on the aggregate or the whole. It will vary because when something will actually decay or break down is a little unknown, but when you get billions of atoms together, it forms a kind of a predictable pattern. And so after one half-life, you've got now half of it. After two half-lives, you will have half of that again, 25%, and so on and so forth. Three half-lives would be 12.5%. You're always seeing half the amount. So that's where the 1/2 is coming from. It is an exponential function as it goes through. And so let's take a look at some of these. Actually, before we do that, let's just, that n, to find that number of half-lives, that's going to be the amount of time that's passed divided by the half-life length. Right, so if, for example, 30 hours pass and the half-life is 8 hours, how many half-lives have actually occurred here? Well, 8, 16, 24, and 3/4. 30 divided by 8 is 3.75 half-lives have actually passed in 30 hours if the half-life is only 8 hours. Just as a quick little example there. Taking a look at question number 1 here. So we've got the half-life being 0.08 milliseconds. Well, after 1 second, what percent is left? In this case here, n is equal to n naught 1/2 over n. And so we're going to figure out how many of these half-lives have actually passed by here. Well, let's take a look. Number of half-lives is 1,000 milliseconds divided by a half-life of 0.8 milliseconds. That means 1,250 half-lives have actually passed. Now, that is a lot of decay that's going to happen here. So the amount we have now, we started off with 100%. And when you actually calculate this, you're going to get a number that's effectively 0, meaning chances are all of this is decayed at this point. It's this metrium-266 is no longer actually present within the sample. It's decayed to other things. Usually students don't have too much difficulty solving for n or n naught, so we're going to focus the rest of our examples on dealing with finding this n because it is an exponent. Okay. 5 grams of the newly discovered Dunbar element has decayed to 2 grams in 0.35 milliseconds. What is the half-life of the Dunbar element? So we first of all need to figure out how many half-lives have actually occurred in this 0.35 milliseconds. Now our equation is this. The number we have now is 2 grams, where originally we had 5. So take 2 divided by 5, gets you 0.4. That's relatively straightforward, but now you're solving for this n. Now there's two ways you can do about this. The first way is graphically. And if you wish to solve it graphically, there is no issue with doing that. Now solving it graphically, type in your calculator, y1 is 0.4, y2 is going to be 0.5 to the power of x, and then you're going to find the intersect of those two spots. And your x value, because your y value is going to be 0.4, will get you what the number is. And if you type that in your calculator, you're going to get 0.6265. Oh, sorry, 1.32. Jumping a little ahead there. You're going to find that's 1.32. Okay. The other way we can do this algebraically is, if you remember from math, your logarithms, we're going to log both sides, which using laws of logarithms gets you this equation. Now again, you can solve it graphically or with logarithms. And so when you calculate that, you get the 1.32 as well. Now, we know that this is the number of half-lives we have, which is the time that's passed, which is 0.35 milliseconds, divided by the time of a half-life. So 0.35 divided by 1.32 gets you the amount of the half-life, or finds that 0.265 milliseconds is the half-life. Okay, so taking a look at example number 3, we've got mercury has a half-life. We've been given the half-lives, and we just want to know how much time has actually passed. Originally, we had 2 grams present. Now there's only 0.38 grams left of the mercury-96. And so if we take a look at that equation again, the amount we have now is 0.38. The amount we originally had was 2. And again, we're going to wind up solving for this n. Now, dividing both sides by 2 gets you to 1/2 n, or 0.19 is equal to 1/2 n. And again, solving it graphically is fine, or solving it using logarithms, and I'm going to just show it with logarithms. Dividing both sides by log 0.5 to get n. And when you calculate this, you find that 2.40 half-lives have occurred. Now, if each half-life is 64.14 hours and 2.4 half-lives have passed by, really you're just going to take that and multiply it by the 64.14 in order to find that this 154 hours has actually passed during this time. Now, let's take a look here at one more example. A lot of this calculations with half-life is how carbon dating happens. Now, there is an assumption on the amount of carbon that was originally present, and over the last little while, it appears that the amount of radioactive carbon in the atmosphere has stayed relatively stable. And so if we've only got 45% of that assumed original amount, n is equal to n naught 1/2 to the n. Now, because again we're dealing with percentages, we've got 45% now, and originally we had, well, 100%. dividing both sides by 100, logging both sides, dividing both sides by log 0.5, that means 1.15 half-lives have occurred. And if each half-life is 5,730 years, that means approximately 6,600 years have passed. So this object is approximately 6,600 years old, according to carbon dating. And again, that's assuming we knew the percent of carbon-14 that would be found within the object would be comparable to what we're seeing nowadays. So hopefully that helps. If you have any questions, please let me know.